notice regarding that?
There is, so at Delhi University will send a circular on the DU's website whenever the classes are supposed to start. Fine.
Okay.
So you will most likely you are going to get notice on the du.ac.in website itself. Even if a circular from the government comes, then Delhi University has to implement it at the university level, and university looks at various factors before confirming it.
Okay, thank you, sir.
So, okay, so let me finish what we were doing in the previous class and then take up a question and other questions which are there from the previous classes, since this is more on the applied portion. So what we discussed in our previous class, in the morning's class, basically, we discussed that one, orthogonal or orthonormal vectors constitute important aspect of the basis vectors, because in the notation of the orthonormal basis or in the orthonormal basis, several things just like the component vectors can be written directly in terms of the inner products, and several other items like the inner product of the two vectors, they become rather simple in terms of, for example, multiplying the coefficients, of course, after taking the complex conjugate. But that becomes rather simple, and hence orthonormal basis becomes useful. So having the inner product allows one to define the length and also allow one to have this orthonormal basis vectors. So before that, we were discussing just about the linear independence of vectors. Now we say that, okay, orthonormal vectors, since we can make that, so let's just use it. Now we are into the procedure that any set of linearly independent vectors can be converted to orthogonal or orthonormal vectors using the projection technique which we learned or which we tried to understand in our previous class, that there is a projection of the vector onto a plane, one, and then there is an orthogonal component of that vector to that plane. So we will utilize that. And how are we going to do it? We said that let's say that we have a basis of n vectors in n-dimensional vector space, which is shown by S. And then I am just defining S prime and S double prime, which is the basis which we would like to make, which will be orthogonal or orthonormal basis. Okay, so we can start from any of the vectors of the linearly independent vector. And what we say that first vector choice is let's just take any vector, but for the sake of convenience, v1 as the first vector which will go in our orthogonal set. What will go in our orthonormal set correspondingly? E1, which is equal to what? Normalize your W1. So that's pretty simple. The first vector you can choose anything. Now, how to choose the second vector? So that should be chosen from V2. And how will we ensure that the second vector should be orthogonal to the first vector? So what should we do? So I should choose my V2 and then what? How to ensure that my W2, this vector, should be orthogonal to W1?
So we can do cross product with E1.
We never defined cross product, remember. We defined projection and the orthogonal component. So remember, we haven't defined anything as a cross product here. We defined inner product, and using the inner product, we defined what is projection and what is the orthogonal component. So what is the orthogonal component of V2, which I want to construct, which should be orthogonal to W1? So what should I do? I must subtract something. What should I subtract?
The parallel component.
Right. So alpha projection of V2 on W1. W1. If I choose this vector, please see in my previous notes, if I choose this vector, what will this vector be? This is the component of the V2 vector, which is perpendicular or orthogonal to W1, when I am going to choose alpha V2, which is the projection of V2 on W1. So what is this alpha then? In the last class we did it. So for those who want to see what we wrote on this page, let me just. Right. So remember that component of V, orthogonal component of V to W was V minus alpha times W, where alpha is W comma V divided by inner product of W with itself. So can you now help me out? V2 minus
W1 comma V
W1 comma V2
V
upon
inner
divided
product of
W1
W1
comma
with
W1
itself.
times W1, or I can also write it as V2 minus E1 V2 E1, because I have already made E1, right? So I could
Yes,
have
sir.
used this one. So please see that this W2, which we have constructed from V2 and the projection of V2 on W1, this W2 is orthogonal to W1. This is by the way of construction. You can try to check it by taking the inner product of W1 and W2. You can do that also, but we have basically tried to show this. Now, how to do then W3? And by the way, the notation which I am using for alpha, generally you will find alpha 21 written, but I wanted to just tell you that this alpha is nothing but the projection of vector V2 on W1. This projection component, if I am removing from this V2, then I am getting the orthogonal component. So let's, before doing the W3, okay, let me just do one more thing, which is constructing E2. So how to construct E2 out of this, which is my orthonormal set.
just divide the magnitude of W2 by W.
W2 upon.
Absolutely right. It's just the magnitude. This is as simple as that, nothing beyond that. So let's just do then W3. So what should I do now? I have to now make this W3 orthogonal to both W2 and W1. So this should be V3
V3
minus
minus
alpha projection of V3 on W1
1.
and subtracting projection of V3
W2.
on
W3 upon
W2.
W2.
Right. And this guy W3, the way we have written it, which is V3 minus, let's just write it. It's rather simple. W1 V3 over W1 W1. This is the projection component of W1, and then write down for this W2 comma W2, right? And you can also write down in terms of orthonormal E1 and E2 vectors. What will be that? Equal to V3 minus
E1 comma
E1 V3, right?
V3 E1 and E2 V3 E2.
Absolutely right. So please see that this particular vector which we have made will be orthogonal to both W1 and W2. And again, you can make your E3 in this manner. So this will be what? This will be again W3. And that's it. And in the same manner, you can continue to construct Wn and En. En, of course, will be rather simple because this is nothing but. And in case of Wn, you will start with Vn and you will continue to subtract how many? So one, of course. So
N minus 1.
right, Vn. So this will be even, so on and so minus E n minus 1 Vn E n minus 1. So please see that the way we have gone ahead with the Gram-Schmidt procedure is nothing but utilizing an important concept of orthogonal projection. We say that keep on removing the projection component and whatever is left with is the orthogonal vector. In this way, we are able to construct a set of vectors which basically ensures for I not equal to j, that is a set of orthogonal values. It is important to note, okay, it is important to note that if you start from any different vector v1, so out of v1 to vn, if you start with v2 as the first vector, then you will get some different combination of the vectors, the actual vectors which you will get. But ultimately, you will be able to build a set of orthogonal vectors or the set of orthonormal vectors where ei, ej will be equal to delta ij. Now, you start with different vectors, of course, you will get different one. Question comes, I mean, this is of course a famous Gram-Schmidt orthogonalization procedure. You must have used it for three-dimensional vector spaces, and this is done for any general one. I'm going to put a numerical at this point of time, and I will discuss with you. But what I want to ask from all of you, in case if I start with linearly dependent combinations, so instead of starting with linearly independent, if I start with linearly dependent set, so let's say I have some set v1 to vn, but such that it is not a basis, it is just that some vectors are linearly dependent. And I try to construct using my Gram-Schmidt orthogonalization or orthonormalization procedure, the set of vectors. What will happen in that case? For linearly independent set, you are going to get, since there were n in the beginning, so you are going to get exactly n such orthogonal vectors. But if you start with linearly dependent, will you still get n linearly independent orthogonal vectors?
At some point we'll
No,
get
sir.
0.
At some point you will get,
Since linearly dependents are exactly that they are dependent vectors, when we are subtracting the parallel components, at some point if they're linearly dependent, we'd get a 0.
at some point
Well,
you will get a zero vector.
yes.
Yeah, so you will still get orthogonal, but then the zero vector comes. So, and once the zero vector comes, you know that that non or that orthogonal set will no longer be useful for making any basis, etc. Because zero vector cannot be part of any basis, right? Remember that zero vector itself, whenever
Yes.
comes, it's a linearly dependent set.
Yes, sir.
Yeah. So if you start with linearly dependent set, then you will encounter that. But I would suggest you do some problem in which a linearly dependent set is there and you try to still make this orthogonal set. Because think about it otherwise. You start with linearly dependent set, and if you n, let's say n such vectors, and if you are able to make n orthogonal vectors out of it, then those n orthogonal vectors will be linearly independent by definition if they are non-zero, right? Because that's the property which we have read, that orthogonal vectors are always linearly independent. So if that is the non-zero ones, so if that is the case, then in no way it should happen that from a linearly dependent n vectors, I should be able to make linearly independent non-zero orthogonal n vectors. So I would suggest that do some problem and try to understand that. That will be a very interesting one. So that you see where are you getting zero vector. Okay, as I promised that I wanted to do a question, so let me just make a question for you before taking up other question. So let's just consider a polynomial space over real field. And since it is P2, what will be the dimension?
2,
3.
3,
Very good.
3.
and I am going to take u1 is equal to 1. Polynomials is it's a polynomial space. I can choose my basis vectors. Will 1x and x square form a basis for this polynomial space?
Yes, sir.
Yes.
Yeah.
Yes, sir.
One thing, please notice that whenever I am not giving you some special vector addition or a special scalar multiplication, it is always the usual one, whichever you use. Yeah. So whenever you do not see vector space with the defined rules of addition or defined rules of scalar multiplication, it means that we are assuming the normal rules. It doesn't mean that there are no rules. It is just that those rules are so normal that we are not stating it otherwise. Okay. So let me define an inner product. So since it's polynomial space, so I have two functions, two polynomials basically. Both of course will have to have a degree less than equal to 2. And I'm trying to define something as this: 0 to 1 fx gx dx. Will this be a reasonable inner product? So first question.
No, sir.
No, sir.
Why?
It will not satisfy the first property of conjugate multiplication.
Conjugate property will not
Okay,
be
tell me the first property. What is the first property? U comma V is equal to V comma U star,
Conjugate.
right?
Oh, sir, it's real number, so it doesn't matter.
Right. So in case it is if it is a real number, then basically this property means this, right? For complex number, of course, you have to be careful. But for real number, it means that U comma V is equal to V comma U. Will not this property be hold true? Fx gx dx is equal to gx fx dx.
Yes, sir, it's true.
Yes,
Yes, sir, it will hold.
Yes, sir,
Yeah.
it will hold
So
true.
this guy, so that is why one has to be careful when one is going in the real space. All the properties which you did in your three-dimensional vector spaces will hold true. There, remember, it does not matter u dot v is equal to v dot u ordering of the vectors before or after this dot. Same thing will be true for real inner product spaces. And you can check your properties, they have to have, in fact. So let's just define this inner product rule. Now let me ask first question. Find for me u1 square, u2 square, u3 square. Of course, I can ask you to give the norm also. This is equal to u1 u1, u2 u2. How will we proceed? How to proceed for u1 u1? So this should be 0 to 1. What is
The integral
1
yes?
square dx.
So
The 1 dx.
1 square.
1 dx.
dx. First function is 1, second function is 1, which means that we are talking about 0 to 1 dx. What is the result?
1
1.
minus
1, sir.
Right? So can you quickly do for me u2 comma u2 also?
1.
Which will 0 to 1 x
1 by
dot
3.
x dx.
1 by 3.
1 by 3.
So 1 by
1
3.
by 2.
1 by 3.
1
X
by
cube by 3, that means 1 by 3.
1
And what will be u3 comma u3?
1 by
1 by
5.
1 by 5.
1 by
1 by
5.
5.
1 by
Yeah.
1
5.
by
Good. So
1 by
first
2.
question done. Second, are these orthogonal vectors? u1, u2, u3. So you are supposed to check what? u1 comma u2, u1 comma u3, and u2 comma u3.
They are not orthogonal.
No,
They
sir, they
don't
are
give
not
0.
orthogonal.
They are
So-
not orthogonal.
So you will find that none of them is 0, but please do find it whenever you are going to do it. And that means they are not orthogonal. Okay, let me just continue with my question. Third part. So I want to find out
Sir, please
matrix.
show
or one value for the previous one?
Yeah, I will show it, but let me just elaborate that question. Matrix representation of inner product in this basis. So remember, it's something I talked about in today's class. Yes, in morning class. So what was the inner product? So I'm going to show it. What is that? Inner product matrix representation. Right. Remember, it is matrix representation, so it is always with respect to a basis. U1 comma U3, and you do not need to find out all the components. Why? Because this matrix is what kind of
Identity.
Identity.
is this? I mean,
This is Hermitian.
they are not. This is not an orthonormal basis. So why will this be ortho identity? What else? We read something else about Hermitian positive definite, which for the real ones become symmetric. So if you find out these three components, of course you have found out these three components as well. U1, U1, U2, U2, U3, U3, you have already found out, right? What was U1, U1? So this was there 1 over 3,
1 by 3
1
and
over
1
5. This you have already found out. So let's just find out U1, U2. Okay. What is the first function? 1. What is second function? U2.
x
X.
X. So 1 into x dx. What is the result?
half
1 by 2.
Square over
1 by
2
half.
into 1 half. So this should go here, right? What about this? U1, U3.
1 by 3.
1 by 3.
1 x.
1 by
1
3.
by 3.
So this should go here. What about U2, U3?
1 by
1 by
4.
1 by
1 by
1 by 4.
1 by 4? No, yes.
1 by 4.
1 by 4.
1 by 4.
1 by 4. So rest of the components you can yourself build. So which one should I put here?
1 by 2.
1 by 2. What about here? 1 by 3.
1 by 3.
1 by
1
4.
by 3. 1 by 4.
So you have got this.
1 by 4.
So this is the matrix representation of the inner product in this S or with respect to the basis which is given to you 1x and x squared. Definitely it's not an orthonormal basis. Yeah. So one more thing. If I want to expand my generic vector, so I am giving you a generic vector 3x squared plus 2. And I want to write down my component vector. What was the component vector, by the way?
V minus alpha.
V minus alpha.
V minus alpha U1. U1.
So component vector should be pretty simple. Alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3. You are supposed to write down that. And your alpha 1, alpha 2, alpha 3, these are the components, right?
Yes, sir.
2, 0 and 3.
So 2, 0 and 3. Right. So what we have done in this example, please see that you have gone up from your regular three-dimensional vector spaces. However, you are using some properties similar to that. So that is where welcome to vector spaces. What we have done here, we have understood that there exists something called basis, and we can write any general vector in terms of the basis. But we have also defined something what we call as the inner product, and we are using that to display some sort of a matrix representation of the inner product. I continued with this question, and this is, let's say, a little bit longer part. So this is our part 5. Starting with U1, I want you to construct orthonormal basis. So I want you to construct E1, E2 and E3 such that this should be an orthonormal one. So you already know what will be the inner product in this, right? 1, 1, 1 and 0 elsewhere. So I want to construct it. How to go ahead with it?
First, we'll take E1 is equal to our U1.
So you say
to
you
make
take
sure that-
W1 is equal to U1 and E1. Remember, this is our first step.
Yes, sir.
Yeah. So what was U1?
1.
U1 was 1. Okay. So is it directly orthonormal vector or no? Norm of 1 was 1 or not?
Yes.
Yes, sir.
In the inner product which was defined to you. So that is rather simple. So this E1 is going to be just 1. What about W2? This is given as what? U2 minus then W1. Let me write it down and let me ask from you whether it makes sense. Fine, no, yes.
Yes, sir.
Anything which is
Yes, sir.
written. Okay.
Yes, sir.
And does it matter for this particular problem whether I am writing W1 comma U2 or U2 comma W1?
No,
No,
sir,
sir.
because it is a
No,
real.
No,
No,
sir,
sir.
because
No, sir.
No, sir.
It's a real space, right? So real spaces make our life simple. So U2 is simple, that is X minus now W1 U2, which is nothing but 1. So U1 comma U2. Have you already solved that?
Yes, sir.
Yes, sir.
It is 1 by 2.
It is
1 by
1
2. It's
Ah.
1 by 2.
by 2. And what about W1 comma W1? Which was U1
So
comma
it's
U1?
1.
It will be 1.
So it's
1.
1. And what is W1?
again
It's
1.
again 1.
It's also
Oh,
1.
1.
so it's 1, which is X minus half. Please see that I could have simply used in this case minus E1 U2 E1, which is basically same as W1 or U1. In this case doesn't even matter. So I can get rid of my denominator part. Let's just write the next one, W3. What should be that?
Sir, we find
U3.
E2 now.
2, 3 minus.
Sorry, can you repeat the question in case if you are asking?
We didn't find E2.
Right, that is a good point. We didn't find E2. So now please help me finding out this norm. And remember the norm, whatever you are finding out, W2 comma W2, this is square root. So don't forget that. Anyway, so help me finding out this E2. So do find out this W2 by
1,
W2.
sir.
Root 1 by 3.
Okay, so what did you have? X minus half square dx 0 to 1. Please do that. So in the simplest case, you can expand it, you figure out what is the number you are getting for W2 comma W2 inner product, norm square.
1 by 12 is the
Under
value
root
of
24.
integral.
1 by 24.
No, just for W2 comma W2. That is the norm square.
I'm getting 1 by 12.
1 by root 24.
1 by 12 or 1 by root 24.
So 1 by 12.
I mean, this cannot be that curve. X square plus 1 over 4 minus x, right? I mean, this is what you are integrating. isn't it?
Yes, sir.
Yes, sir.
So this should be x cubed by 3. This should be 1 by 3 plus 1 by 4x, which should be 1 by 4
1 by 4.
minus x square over 2, which should be 1 over 2, right?
Yes, sir.
And that's what you have done. I mean, you could have taken LCM here itself, or so what are we getting now? 7 minus 6 over 12, right? Is it that?
Yes, sir. Yes, sir.
Yes, sir.
So that means 1 over 12 makes sense. And what will be the norm then? Is
Root of 1 by 12.
so 1 over root 12. And that will make our E2 as, so what will be our E2 then?
Root 12 into x minus 1 by 2.
All right, root 12 x minus 1 by 2. Okay. What about W3? It is U3 minus what? Which component I'll have to remove?
Both first W1 minus W1 U3
Okay,
And then W3
by W1 W1
W1 and
to U3.
W2 U3
W2 U3 over W2 W2,
W2.
right? And W2. And please do this as the homework exercise. It's not tough, but what you will see an interesting aspect, that even though the orthonormal bases are generally used with our three-dimensional vector spaces very regularly, but it is something which doesn't look that obvious for the polynomials or set of polynomials. So as you have already seen that your second polynomial, when you are starting with the first one, okay, that was simple, which was only one, this one. But second polynomial doesn't look that obvious. It depends on what is the integration limit. In this case, it is 0 to 1. Sometimes it is minus 1 to 1. Sometimes it is very different from these. So for the polynomial basis, even though orthonormal basis becomes for the polynomials, vector spaces, even though orthonormal basis become very important, but you may not use it. You may give it up in favor of something which looks rather more simple, which you can evaluate using your laws of inner product. But I will still ask you to do that, and not only that, do question number 6 also, which is expand that same vector. Remember a vector which I gave you on the previous page, which was 3x square plus 2. So let's say there exists a vector 3x square plus 2. I want to have the same vector now written in terms of this orthonormal basis S prime, which is what you are constructing. E1 is 1, E2 is this root 12 x minus 1 half, and W3 we haven't yet found out, and you are going to find out in your homework. After that, you are going to do basically this expansion, because then you will have your all the orthonormal vectors being set. So this is one example of basically taking care of or applying our knowledge of Gram-Schmidt orthogonalization procedure in the vector spaces, which are the continuous ones, the polynomials ones. And the reason why I'm using the word continuous, even though polynomial spaces are not exactly, because of the famous Weierstrass theorem that any continuous function can be written in terms of the polynomials of arbitrary degree. But anyway, I mean, as long as you can do it in the polynomial functions, it is fine for me. Okay, questions here so that I go to the next important point related with the inner product.
Sir, can you please repeat what we have to do in the sixth part?
Oh, once you get your E1, E2, and E3, this is your new set, right? This is the basis.
Yes, sir.
So write down the vector, this vector, generic vector of this space. Remember, this is a generic vector of the P2X, any generic one, in terms of this new basis. which is the orthonormal basis which you have constructed. Yeah.
Yes, sir.
And that will also tell me that anytime your basis is changed, if you are going to write down your vector in terms of the components, make sure that you handle your basis very carefully, because if you change the basis, the same vector will look very different. It is equivalent to saying something like this. So if I give you this vector, just like this, and I ask you to find out the components, how are you going to find out the components? And this has vector direction, this has point. So how will you find out the direction?
So we need the coordinates or the system we're using to measure the
Right. So you say, sir, there is a possibility that I can use this kind of a system, and then I will give you the coordinates or the components with respect to this system, or otherwise I can actually, I mean, I could have given you a system like this. Who knows? Which is some sort of a rotated system with respect to this. And I will ask you to find out the now components with respect to this new system. So unless this coordinate system is defined, I cannot simply write down this vector in terms of anything. And hence this saying that we should write vector in terms of this I plus j plus k, that doesn't look as a valid definition of a vector actually. Because it depends from which origin I'm talking about. When we talk about the magnitude and direction, direction is with respect to some coordinate system. So it's not the commonest definition of a vector at the post-graduation level. So I should ask you, okay, what will be the commonest definition of vector then in that case? How to distinguish it from a scalar or maybe something other, some other quantity? Big question, but if you answer that question, then carry on that definition of the vector with you forever, because saying that the vector has magnitude and direction looks fine at the 11th, 12th level, or maybe at the undergraduate level also. But at the postgraduate level, once we understand that it is dependent on the choice of the coordinate system, and saying that we are talking about direction, with respect to what we are talking about, which direction? So then suddenly it gives some confusion. So in order to avoid that confusion, there should be a better definition of the vector. And that definition I am just going to ask you to look at in some standard text. In case if you are unable to come up with this, you are going to come back to me and then we will discuss it again. Okay. I wanted to do something else which is equally important with inner product. First I said that it defines the concept of length. As soon as it defines the concept of length, we have this normalization of the length, and hence we are able to now think about psi star psi kind. Then we say that we can also use that concept to make orthonormal basis, which will be a very useful basis whenever the product has to be taken, inner product has to be taken, or the scalar product has to be taken. So that inner product allows us to not only just do xi star xi, but also define the set, which kind of basis vector you should choose, so that it looks rather straightforward to write it. As we have a habit of writing vectors in terms of component, abstract vector in terms of the component matrix. Okay. Another concept which becomes very important is direction or angle of the vector. Now, if two vectors are given to you and I ask you what is the angle, which is what we discussed last time, we say, okay, it is A dot B over A dot, something like this, right? So do we have something similar for the abstract vector space? And this results in a very important identity, which is called Cauchy Schwartz, or sometimes just the Schwartz inequality. So there is a famous inequality which will come from Cauchy Schwartz, which will help you in generalizing your Heisenberg uncertainty principle. What is the Heisenberg uncertainty principle, which you have read?
Delta x delta phi greater than equal to h bar by 2.
Right. Okay. Absolutely right. So this Heisenberg uncertainty principle, you are going to now generalize it in your quantum mechanics class. And this generalization comes from very important inequality, which is called the Cauchy Schwartz inequality. So let's just do that, and this will help us defining our direction.
So do
Or
we
actual-
require
Yes.
do we require this inequality in while solving the light cone problems too?
See, light cone problems, depending on what kind of light cone problems you are talking about. If you are talking about a special theory of relativity, then what you are
Yes,
going to, then where you are going to go is what we call as the Minkowski space generally, or some similar space for the four vectors. Yeah,
yes, sir.
I am not going to go in detail, but let me just summarize for you a very important, metric which comes there is written in terms of 1 minus 1 minus 1 minus 1. Those of you who can understand it is fine. Those of you who cannot, it is fine because it is not, or something. Okay. Something like this, minus 1, 1, 1, 1, 0, 0. Can you relate this 3 minus 1s or plus 1 plus 1 with anything? When you multiply your four vectors, remember?
Sir, is this
You have
x,
a
y, z, and minus ct?
right. So let me just write it down for you. Oh. So remember when you are taking the four vector product, so you define four vector as something like ct, comma, x vector, and then x mu ct minus x vector. I mean, this is a typical way of defining a four vector, and then you take the product of the two. That can also be written in terms of matrices, and the matrix which comes there is of the type this 1 minus 1 minus 1 minus 1, which you can take as the coefficient which is coming from here, right? Or in terms of defining it as the first component, I mean the vector components being positive and this time component being negative. So which space you are talking about, we will have either this or that. The only problem with this or that, I mean, this is a very valid thing for special theory of relativity. But in terms of what we are doing, there is one problem in this kind of a metric, that this is not a positive definite metric, right? Because you have minus 1 in the off diagonal ones. So
Yes,
here
sir.
also there is minus 1. So this will not directly help you there, but you can build a Cauchy Schwartz inequality kind of inequality there in the special theory of relativity, assuming that you understand how to get this. But I will leave it to your electrodynamics class for the time being, that how they are going to teach, except that it is an important extension of our linear vector spaces, where we do not define our inner product in a special sense, in that sense in which we defined, which is defined for the quantum mechanics, but we define it in certain manner so that we can take care of this kind of metric also. Fine. So it's not directly, but yes, it can be extended. Did I answer the question? I mean, even though I
Yes,
have.
sir.
Okay, thank you. So let me just tell you from where we start. Since we are going to talk about a general inequality in any vector space, so let's say two vectors, these belongs to some complex inner product space, and I have one of this scalar which belongs to a, of course, complex space, so it is a complex number. And the starting point for this is rather simple. So I will talk about this guy, u plus alpha v. So we have, I am talking about two vectors and I am taking linear combination u plus alpha v and then norm square. Do we have some property for this? Any rule which will tell me something about this kind of a vector or any vector? Will this be a part of the complex inner product space u plus alpha v? U is a part, v is a part. Will u plus alpha v will be part?
Yes, sir.
Yes, sir.
By the definition, I mean, this is the vector addition and then the scalar multiplication. This have to be. So when, if it is part of the same product space, then what will be the rule for the norm square? This should be
It should be greater than equal to 0.
absolutely right. This should be greater than equal to 0. So let's just write down this. So u plus alpha v comma u plus alpha v should be greater than equal to 0. Now expand this bracket in the manner in which you know it. So u comma u plus
alpha u comma
Alpha
v.
okay,
u
let me
comma
just alpha u comma v plus
alpha conjugate sorry,
Conjugate
alpha
V.
conjugate vu.
alpha conjugate
v
v comma u plus alpha conjugate alpha v comma v should be greater than equal to 0. So this, if I define it, some quantity which is a function of alpha, we want this inequality, this has to be, because this is the definition. This guy which is on the left hand side must be greater than equal to 0, or in other words, I should say that whatever the minimum value of this I alpha we find, that minimum value should also be greater than 0, then only this will be hold true for everything, right? So that left hand side should be greater than equal to 0 all the time. So if we find out the minimum value of I with respect to alpha, then that should be greater than equal to 0, because any value greater than that will of course be greater than 0, surely. So we are supposed to find out minimum value, and that is the reason of introduction of this alpha. Let's try to find out the minimum value of I alpha for which this inequality holds true. Minimum value of I alpha for which this inequality holds true. How will we find minimum value? How do we find extremums?
Differential.
We differentiate with
Put it equal to
what?
0.
So di over d alpha equal to 0. So let's just do that in order to find out the minimum value of this I alpha. So please find out, do the di over d alpha and equate it to 0 to give me whatever you are getting. So I'm keeping this page open and then I will let you do this. Di over d alpha. Remember, every triangle bracket is nothing but a complex number, nothing more than that. In some cases, it will be a real number. So, okay, what is the di by d alpha you got? So, first term 0, second term
U comma v.
u comma v, third term
0.
0.
0, fourth term
Alpha
Alpha
star
star
V comma
V
V.
comma V.
alpha star v comma v. Okay. This has to be equated to 0. So what is alpha star?
Shit. Oh.
Okay. Yeah, this is unfortunately the downside of our online classes. Anyway, so what is right? What about alpha then? How to find out this?
Sir, by differentiating with d alpha star.
Oh, you do not need to, because you have already got alpha star. So how do you
Sir,
find the
it
complex
will
conjugate?
We can take the conjugate of
So it's just
the
the
first equation.
common conjugate.
Which will be what?
Conjugate.
So remember
V
that the
comma u
denominator
star
is a real
upon
number
V
all the
comma v
time.
star.
So this guy is always a real number. It is only the numerator. So u comma v star, which will be
V comma U.
v comma u. Right. So let's just put these back in our original equation. So now let me do some work for you. So this term remains same. Then what was the term which we wrote? So alpha times u comma v. What is our alpha? This is v comma u over. And then u comma v. Next, what is the next term? Alpha star v comma u. So what is alpha star? Let's write uv over v. This is v comma u. And what will be the last term? Alpha into alpha star. So let me just first write down this and two negatives. So this will be positive u over v comma v comma u over v comma v, and last term would be v comma v, which is greater than or equal to 0. Now, okay, this looks interesting. So this guy will cancel with this. Now, what will happen? What are we left with? U, of course, and this guy, u comma v into v comma u divided by v comma v. Does this cancel with any other term? No, yes. Remember, these products are all only complex numbers, so you can always move it around here and there, just like the way you do the complex numbers multiplication. But in this case, you do not even need to. U comma v comma u divided by v comma v, and look at this term. So this guy goes ahead with this, and you are left with v comma u, v comma v, u comma v greater than or equal to 0, or I can write down u comma v, v comma u. So please tell me. So u comma v, v comma u should be less than or equal to
U comma U.
u comma u
into v comma v.
V comma
into
V.
v comma v.
into v comma v. Absolutely right. Now remember, this guy is nothing but u comma v star. So I can write down this as u comma v complex number square, which is less than or equal to first term norm square of u, second term norm square of v. So just take it to the next page, since everything now is written in terms of the positive quantities. So I can just take it to the next one and I can write down u comma v be less than or equal to u times v. This is what we call as Cauchy Schwartz inequality, and you are going to also get it in your tutorial to emphasize its importance. There are other inequalities which also get built up, but this inequality is very useful. Now, remember I said that it can be related with the direction. How? U comma v this quantity should be
Equal to the dot angle of the dot product that we can take out between the two vectors.
so taking from here, this quantity is just this, right?
Yes.
Yes.
And defining cos theta to be like this. This is the way we define our theta. You see that what we are doing, we are writing cos theta should be less than or equal to 1, which is basically true for. So this way you can define your cosine angle, except that in the non-real spaces, that means in the complex spaces, you will say, sir, the numerator you will get as a complex quantity. And what to make out of it when I am going to relate complex quantity with an angle? That will be difficult to think of. Yeah, surely in the real spaces, this will work exactly. I mean, this is works just like a charm, because you know that you can always define an angle there. So what do we get? We get a very generalized inequality in the case of inner product spaces, which is called a Cauchy Schwartz inequality. This inequality you are going to use for your Heisenberg uncertainty principle, and that you are going to do in your quantum mechanics. This in the real spaces can be used to define the angle, just like the way you define angle in the three-dimensional vector spaces. So this is what I wanted to say about the Cauchy Schwartz inequality. If I ask you to write down, okay, I mean this inequality, just to see if you have understood this inequality, and can you just write it down for me? Nothing beyond that. So I give you, let's say, polynomial spaces again, and I say fx gx inner product. Now, since it's a complex inner product space, so even if I define it 0 to 1 or a to b, I will have to write down this, right, to ensure that I get my rules correctly implemented. So if I define like this, please write down either this portion or the square of this one, the one which was written on the back side. So what should I write? Just help me out. Left hand side. So 0 to 1 f star x gx dx mod square should be less than equal to what? 0 to 1.
Sorry,
F star x fx.
What will be that? Mod of fx square dx,
Not
right?
FX. Yes.
0 to 1.
Gx square dx.
Yeah.
Yes.
Please, the reason why I wanted to write it, even though in the generalized form it is very simple to write it, but I find that students struggle while working it out with various vector spaces. And hence I want to explicitly write down. In fact, I want to expand the question which I asked in the beginning here, which I was doing up to this place, up to point number 6. So remember the question which we were dealing? Oh, God. So previous, this one. Yeah. So we have the polynomial spaces. I want to ask for this question to check. So this is the extension. Check CS inequality for this new space, for the original space which you've had, u1, u2, u3. Remember this was 1x x square. For orthonormal one, you will always find it to be true. For orthonormal space, uv will be equal to what? Inner product of uv, orthonormal, two different vectors.
0.
0. And
Zero.
what will be the right hand side?
1.
Norm.
1.
1. 0 is
1.
less than equal to 1. Fine. All the time 0 is less than 1. Absolutely fine. But for generic vectors, I would like you to find it out. This is one. Last question on this part. When is this equality sign hold true? So there is this strict less than and then equality. When will this strict equality sign hold true? That uv, yes.
When the vectors are equal.
Equal, do you want equal or something else? See, remember we started with what? We started with this kind of a vector, right? And we said that this is equal greater than equal to 0. When will this guy be exactly equal to 0? When? When this guy is 0 vector, in that case, your equality sign will hold true, right? This is the by definition. What does that mean?
So one vector is a multiple of the other vector.
Right. So
Yes.
this means that
each other.
so this will be right dependent on each other or multiple of each other. Or you can say that a line when it is parallel to each other, it's fine for me. But one, please understand that in this case, when we are writing like this, we are able to write one vector in terms of other vector. So it may be a linear dependent term. So whatever way you figure out. But please understand that this equal to 0 will work out whenever one vector is proportional to other vector multiplied by, of course, by a scalar alpha. Any multiplication by scalar does not matter. Just like the way you understand in three-dimensional vector space, you multiply a vector by any number, it is just going to scale up or scale down, but won't change the direction. Yeah. So anything else on this part? No. So I mean, I basically covered inner product spaces, and I'll discuss the summary in tomorrow's class. Something which I asked, I mean, just not quick question. I asked for this, any inner product rule for matrix space. Did you try to make up or figure out? This is what was asked in the last class. I tried to figure out the inner product rule. I gave it for the polynomial, I gave it for the n-tuples, but I did reserve this one. So please do try to figure out. Questions on anything done in now this class or previous class in the morning class?
Sir, can you go
Yes. Can I go?
back 2 slides? I
Previous one?
just back.
One more?
Yes, sir.
Here?
Done, sir. Okay. Thank you.
Oh, but can I ask you a question? Sorry, I mean, this is good that you have reminded me. When you took the differentiation with respect to alpha, what did you do about alpha star?
Considered it as
Consider that to be independent of alpha.
of alpha.
So can you consider alpha star to be independent of alpha? Good. Okay, generic question. Very good generic question. Can you consider that? Oh, you did rightly consider it, by the way. This is what I have already said. I mean, you have rightly considered it. There is nothing wrong. How to prove that these two are independent? How? The simplest one, I mean, you can always try. I mean, is if you have any issues, always write it in terms of this and see what will be the coefficients. If C1 and C2 are zero, identically zero, then of course alpha and alpha star can be treated as independent. This is the simplest. So how to go ahead? So let's just do something like this: x plus iy plus. This is the simplest mechanism through which you can check. So C1 x here plus C2 x here. So coefficient of x equal to 0 and coefficient of y. What will be that? C1 minus C2 equal to 0. What will these two give?
C1 equals to C2 equals to 0.
C2 equals to 0.
Yeah, I mean, you can add those, whatever you want to do. I mean, you will figure out that this will be equal to 0 and you will be able to say that, okay, I mean, at least in terms of the first principles, these alpha and alpha star are independent of each other. This is a simplest way of showing that alpha and alpha star are independent. There are other ways of speaking about the same, but do try to read about these things. I mean, that is why Balakrishnan book, this is an excellent text. This remember V. Balakrishnan, this is the first text which is written as the reference. This is an excellent text on these things. Particularly, he's an excellent teacher. If you figure out certain YouTube videos, you will see the way he explains things. Maybe at the later stages, you can follow it once you have some idea of your MSc or the basics of the MSc. And then the book also is written in that style, that it is trying to explain several concepts from maybe from the basic side, but taking care of it at the advanced level. So the question which I asked, for example, the vectors, what should be the definition of the vectors now that the direction is with respect to coordinate system? You can try to just look at it from the same book and see if you can get something out of it. So yeah, I will recommend reading the Balakrishnan book also whenever you get some time. Okay, thanks.
Thank you, sir.
Okay, sir.
Thank you,
Yeah.
sir.
Thank you, sir.
Yes, sir.
Thank you,
Bye.
sir.
Thank you, sir.
Yeah, bye.
Thank you.